Lambda function in list comprehensions. Why is the output of the following two list comprehensions different, even though f and the lambda function are the same? And mind you, both type f and type lambda x column xx return the same type.
The first one creates a single lambda function and calls it 10 times. The second one doesn't call the function. It creates 10 different lambda functions. It puts all of those in a list. To make it equivalent to the first you need, or better yet,
this question touches a very stinking part of the famous and obvious Python syntax. What takes precedence, the lambda, or the for of list comprehension? I don't think the purpose of the op was to generate a list of squares from 0 to 9. If that was the case, we could give even more solutions. This is the good old way of imperative syntax. But it's not the point. The point is WTF, is this ambiguous expression so counterintuitive? And I have an idiotic case for you at the end, so don't dismiss my answer too early. I had it on a job interview. So, the ops comprehension returned a list of lambdas. This is of course just 10 different copies of the squaring function. See. Note the memory addresses of the lambdas, they are all different. You could of course have a more optimal, version of this expression. See? 3 times the same lambda. Please note that I used underscore as the for variable. It has nothing to do with the x and the lambda, it is overshadowed lexically. Get it? I'm leaving out the discussion, why the syntax precedence is not so, that it all meant. Which could be 0, 1, 4, ... 81, or 0, 1, 4, ... 81, or which I find most logical, this would be a list of one element, a generator returning the values. It is just not the case, the language doesn't work this way. But what if? What if you don't overshadow the for variable, and use it in your lambdas? Well, then crap happens. Look at this. This means of course. But it doesn't mean. This is just crazy. The lambdas in the list comprehension are a closure over the scope of this comprehension. A lexical closure, so they refer to the I via reference, and not its value when they were evaluated. So, this expression is roughly equivalent to. I'm sure we could see more here using a Python decompiler, by which I mean for example the dis module, but for Python VM agnostic discussion this is enough. So much for the job interview question. Now, how to make a list of multiplier lambdas, which really multiply by consecutive integers? Well, similarly to the accepted answer, we need to break the direct tie to I by wrapping it in another lambda, which is getting called inside the list comprehension expression. Before. After. I had the outer lambda variable also equals I, but I decided this is the clearer solution. I introduced Y so that we can all see which is which. Edit August 30th, 2019. Following a suggestion by Joe Solar, which is also present in an answer by Sherip, the value of the list comprehension loop variable can be embedded inside an object. The key is for it to be accessed at the right time. The section after above does it by wrapping it in another lambda and calling it immediately with the current value of I. Another way, a little bit easier to read, it produces no what effect, is to store the value of I inside a partial object, and have the inner original lambda take it as an argument, pass supplied by the partial object at the time of the call, i.e. after 2. Great, but there is still a little twist for you. Let's say we want to make it easier on the code reader, and pass the factor by name, as a keyword argument to partial. Let's do some renaming. After 2.5. What? Wait. We're changing the number of arguments by 1, and going from too many to too few? Well, it's not a real what. When we pass coef to partial in this way, it becomes a keyword argument, so it must come after the positional x argument, like so. After 3. I would prefer the last version over the nested lambda, but to each their own. Edit August 18, 2020. Thanks to commenter Daswesen, I found out that this stuff is covered in the Python documentation. This URL, it deals with loops instead of list comprehensions, but the idea is the same, global or non-local variable access in the Lambda function. There's even a solution, using default argument values, like for any function. This way the coef value is bound to the value of I at the time of function definition. See James Powell's talk top to down, left to right, which also explains why mutable default values are shunned.
The big difference is that the first example actually invokes the lambda fx, while the second example doesn't. Your first example is equivalent to lambda x column xxx for x in range 10, while your second example is equivalent to f for x in range 10.
The first one runs f for each value in the range, so it does fx for each value. The second one runs the lambda for each value in the list, so it generates all of those functions.